Hello, good morning. Okay, so let's start the class now. Today we will finish the discussion on methods of proving, and then we are going to talk about proof by construction. So proof by construction is usually used in showing something that exists. So we are trying to prove that something works by constructing an example that it works. So in particular, in a lot of geometry problems, and then we can use some creative line that we draw so that we can show that something works. And here we have some examples. The first one is this one. We define what is meant by a k-regular graph. So a regular graph is a graph such that each vertex has the same number of incident edges. So each vertex has the same degree. So for instance, this vertex, all these 5 vertices, we have degree equal to 2. So this is a regular graph. And for this one, each vertex has degree 3. So it is also a regular graph. So a k-regular graph is just we add a specific description of how the degree is. So a k-regular graph is a case where each vertex of the graph has the same degree k. Okay, we have defined what is meant by a k-regular graph, and we want to show that for every even number n greater than or equal to 4, there must be some graph with n vertices, and it is also 3 regular. So how this can be shown? If somehow you can, for every n, you can draw a certain graph that is 3 regular with that number of vertices, then we're done. And then this is actually not a very difficult problem if you start by working out some simple examples. So for instance, this is a case where n is equal to 6. In fact, okay, one easy way to draw a graph with this property is we draw we list out all the vertices on a circle, and then we form a convex n-gon by joining the neighboring vertices by an edge, and then we draw a diagonal, that is for each pair of vertices we join them together across the center. So it's like this. For there are 6 vertices, we join these 2 together, join these 2 together, join these 2 together. We join the vertices that are at opposite location on the circle. So in that case, we can easily check that it is a 3 regular graph. So this is a way that we show the existence. Now another way is this is also a proof by construction, but this time this is a super interesting example that I borrowed it from the undergrad discrete math class. We want to show that we can find irrational numbers Q and R. Q and R, they are both irrational, such that Q to the power R is a rational number. Okay, it looks like very strange. We start by irrational, and then the power is also irrational. But interestingly, we can have some kind of situation that the resulting number will be rational. So how can we show? What we are going to show is like this. We are going to consider this value. This is square root 2 to the power square root 2. This is a single number, and then to the power square root 2. Now, if you use our algebra or arithmetic, then we can find out that square root 2 to the power, okay, we have x to the power y and then to the power z is equal to x to the power y times z. So in that case, square root 2 to the power square root 2, this number to the power square root 2 is the same as square root 2 to the power square root 2 multiplied with square root 2. And because square root 2 multiplied with square root 2 is equal to 2, so square root 2 to the power 2 is equal to 2 as well. So in that case, the value here that we are seeing is exactly equal to 2, which is a rational number. Okay. Now it works, right? So this number looks like an irrational number, and this number looks like this number, we know it is an irrational number, right? So in that case, we have an irrational to the power irrational, which is equal to 2, which is rational. However, the discussion I just gave is wrong. Yeah, because what I'm saying is this number looks like irrational. What if it is rational? If it is rational, then it cannot be used as our Q, this cannot be used as our R to show something that works, right? But on the other hand, if this number, which is not very likely, but let's say this number turns out to be rational, then again, we have something nice to happen. We can treat square root 2 itself as Q, we can treat this square root 2 itself as R, so that in that case, we have irrational to the power irrational becomes rational. Okay, so in conclusion, we have two cases. One is this number itself is irrational. If this number is irrational, then this number to the power square root 2 becomes rational, so we are done. On the other hand, in another case, this number itself can be rational already. Then in that case, we choose this one as the irrational number, this one as the irrational number, so we still have irrational to the power irrational, which becomes rational. Either case 1 or case 2 occurs, and no matter which case that happens, then we get the same conclusion. So in that sense, yeah, it is true that we can find certain irrational to the power irrational, which is rational, although we don't know the Q and we don't know the R, but it exists. So this is a construction, proof by construction, but this is kind of an implicit construction. And then perhaps this is the most proven theorem so far in the whole world. Okay, the Pythagoras theorem. So we are claiming that when we have a right-angled triangle, and the length of the sides are A, B, and C, where C is the longest one, what we call the hypotenuse, then we must have A squared plus B squared equal to C squared. And then there are so many proofs. So this is the one that I learned when I'm in the primary school. So we draw 4 of these ABC triangle, arrange them to become a big square. So we can see that the inner part itself has to be a square. Yeah, because we can look at the angles here, so that we can deduce the angle here must be 90 degrees, and then we can infer that the sides of these quadrilateral are all the same, so it must be a square. Okay. Now in that case, we can compute what is the area of the big square in 2 ways. This is a combinatorial proof. So the big square has area A plus B to the power 2, because one side is A, the other side is B, so A plus B is the length of one side. So one way that we can count the area is A plus B whole square. On the other hand, we can count the area by looking at the total area formed by the little triangles, which is 4 times AB over 2, plus the middle square, which is C square. So we know that this is equal to this one. So after simplification, we will get A squared plus B squared is equal to C squared. Okay, so this is an existence proof. This is a non-existence proof. This is a proof by construction. We start with a triangle, but then somehow doing some creativity thinking, we can link up the area of the triangle and the little square and the big square together. Okay. And then we have another example. Now this one I read it from a book written by a professor from NTU. And then in his book, he gave this example. We want to show that the inverse of tangent 1/3 and the inverse of tangent 1/2 adds up to 45 degrees. Now notice that this is a value. So inverse of a tangent is an angle. So this angle plus this angle is equal to 45 degrees. So how do we show? Okay, what we are going to show is we draw a triangle with a right-angled triangle with height 1 and then with 2. So it is a 1-2 triangle. We place it here like this. We also place it here like this. So, and then we join these 2 lines together. So in fact, this is half of the shape that we are looking at here. Okay. Now, we don't actually need to find out or remember the formula for tangent inverse. It's not needed. As long as you understand what is meant by tangent inverse, that's okay. So tangent inverse 1/2 is what? It is this angle. Is that okay? Or this little angle, this sharp angle. Now how about tangent inverse of 1/3? So in order to get tangent inverse of 1/3, we want to have a triangle such that the height is 1, the width is 3, and then we measure the angle of, opposite to the short edge. And then from this figure, we see that this is the height 1, because it is 1 by 2, so this is 2, so this is 1. 1 by, what is it? This is 1 plus 2, which is 3. So actually, this angle is tangent inverse of 1/3. And then this angle is the same as this angle. So this angle is tangent inverse of 1/2. So the summation of these two angles is exactly this angle. And now what is it? This is half of a right angle. This was a square, right? This is half of a square angle. So this is 45 degrees. So we're done. So you can draw other examples, like maybe you can have a triangle, like this is side 2, this is 5, and so this is 5, and then this is 2. Then we can have tangent inverse of 2/5 plus tangent inverse of 3/7 is equal to 45 degrees. Okay, so you can draw many different examples as you like. Okay, the last example that, okay, not last, but then proof by construction, one famous thing is we can use it to show something is a countable set and something is not a countable set. Okay, so we define countable set. So this should be something that you have already studied in the discrete math class, but let me review it. So a set S is countable if there are two cases. One is the size of the set is finite. And then the other case is the items in the set can form a one-to-one correspondence with the integer set 1, 2, 3, 4, 5, blah, blah, blah. What does that mean? So the word countable means that we can count out the items, all the items in the set S. So we can count out, let's say this is the first item, and then this is the next item, the second one, this is the third, this is the fourth, this is the fifth, and so on and so forth. There is a way that we can count out the items in S one by one without missing. Okay, if a set has this property, so if it is finite, then we must be able to count the first one, the second one, the third one, and so on and so forth, right? Or if there is a one-to-one correspondence between the integer set, so this is naturally, this defines the way that how we count. If it corresponds to 1, this is the first item that we count. If it corresponds to 2, this is the second item that we count, and so on and so forth. Okay, so we want to show that the following examples are countable sets. So for instance, all the even numbers. The set of all the even numbers is a countable set. So how can we list out all the even numbers one by one without missing? We can do so like this. We can first list 0, and then 2, and then -2, and then 4, and then -4, and then 6, and then -6, and so on and so forth. We don't need to know for us, let's say the number 100, when will it be counted? We don't need to care, as long as we know that it must be counted somehow. Notice that each time we are advancing one positive number and one negative number, right? From small to large. So eventually, we will hit, let's say 100. We will hit -700. For any integer that is even, we will be hitting it somehow, sometime in the future, in finite number of steps. So in that case, we have established the fact that all the numbers inside this E can be counted out, so it is a countable set. Now the next example is the set of all the prime numbers. So we have 2, 3, 5, 7, 11, 13, and so on and so forth. So how can we show that it is a countable set? It's fairly easy. We are going to count out the primes by counting them from the smallest to the to increase in increasing order. So we first give the smallest prime, and then the second smallest prime, and then the third smallest prime, and so on and so forth. So in that sense, no matter which prime number you are talking about, let's say I'm looking at the prime number 101. I know that 101 is at most the 101th smallest prime number, right? Yeah, because there are only 101 numbers before it, right? Including itself. So in less than or equal to 101 steps, we must be counting this number out. So eventually, we must be counting the prime number 101 in some time. For any prime p, it will be counted in finite number of steps. So in that sense, we also know that P is also a countable set. Indeed, whenever we are talking about a subset of a countable set, then it must be countable. The reason is that because originally the countable set tell us that, okay, the numbers inside, or not the numbers, the items inside this set, you can give them labels 1, 2, 3, and so on and so forth. If I have a subset, then I can talk about, oh, what is the smallest one that is still kept in this subset according to the labeling in the original countable set? Is that okay? What is the second smallest item that we are keeping in this subset according the label to of the original countable set? So in that sense, we can list out all the subset items here one by one according to the label originally we give when we show that it is a countable set. So in that sense, if I know 3 originally, then because the natural number set obviously is a countable set, so in that sense, we can immediately show that P is also a countable set. And the fourth one is a pretty interesting example. So we are talking about all the rational numbers, they are countable. So in order to show this, so I would suggest you to take a look of the OCW recording. So in particular, before we show that the set of all the rational numbers, this set is countable, we can show, okay, so assume that we are talking about a different question. So let's look at the grid points in the first quadrant. So we draw the x-axis, we draw the y-axis. So after that, we look at the points with labels, with coordinates x, y, such that x and y, they are positive integers. Okay, let's take a look at this one. Or let's say x and y are non-negative integers. Okay. Okay, so we have the points 0, 0, 0, 1, 0, 2, 0, 3, and then we have the points 1, 0, 1, 1, 1, 2, 1, 3, and so on and so forth. We claim that the set of points of this form, this will be an infinite size set, right? The set of points in this form is a countable set. The reason is we can have a way to count out the points one by one without missing them. So we count so let's say we have a, it's better to look at the OCW recording for reference. But the idea here is that, let's say we have the x-axis, x-axis here, and then the y-axis here. So we start counting the origin 0, 0, and then we count the top one, the right one, and the bottom one. So we count 1, 0, 1, 1, and then 0, 1, and then we further count another level. It's like peeling onion, but then we are from center to outside. So we count 2, 0. Is that? Let me see. We count what? We count something that adds up to 2, right? So we count 2, 0, 1, 2, and then 2, 2. Sorry, 2, 0. Sorry, we count 0, 2, 1, 2, 2, 2, 2, 1, and 2, 0. It's like we count things like this. So in that sense, we can say all the points will be counted somehow. And there are numerous ways of counting, or numerous ways of doing the enumeration. So one way that I'm showing is like this, but there is another way that you can count the diagonals one by one. So in any sense, the set of grid points with non-negative integer coordinates. So grid points are having integer coordinates. The set of grid points such that the value of each coordinate is non-negative is a countable set. And somehow after that, we can relate this with Q and show that the set of all rational numbers is also countable. Now, given a lot of examples of countable sets, so it looks like, oh, is it true that everything is countable? Now, this must be no. Okay, this must be no. Otherwise, we won't have a concept of countable defined, right? In particular, we want to show that the set of real numbers, all real numbers, is not a countable set. In order to show this example, so we are not going to prove directly R is not a countable set. We focus on only a subset of R, the real numbers in between 0 and 1. We focus on all the real numbers inside this range, and we want to show that the set of all real numbers inside this range is not countable. Once we show this, then we can show the original claim. Why? Why is it true? The reason is that this is a subset of this one, right? If this is countable, then this is countable. So if this is not countable, then this is not countable. So this is the contrapositive argument. So in order to show this example, we are now just focusing on all the real numbers between 0 and 1, and we want to show them it is not countable. To do so, we are going to show this by contradiction. So assume that, on the contrary, this set of numbers is a countable set. Now, if this set of number is countable, then there must be, so we call this set R prime, okay? So there must be a one-to-one correspondence between the numbers inside this set and the integer set. Now, because of this, then we can list out the numbers. So there is a certain one-to-one correspondence. So if it is true, then you tell me, okay, because there is a one-to-one correspondence. So there must exist a certain one-to-one correspondence. So let's say there is a God or there is a genius who can tell me, oh, let's take a look at this one-to-one correspondence, and it works. Okay, so in that case, we start from our genius's advice or the God's advice so that we know there is a one-to-one correspondence between the real number between 0, 1 and then the integer set 1. So in that case, we can talk about what is the first one? What is the real number that corresponds to the first number? So we call this the first real number here. So maybe this is this number. Is that okay? Maybe this number. And then we can talk about, what is the second real number? So this is the second real number, right? And using the one-to-one correspondence, we can list out all the real numbers here one by one. And now what we are going to do is, let's take a look of a special real number, x. This special real number will be constructed. Now, this is the construction part. Will be constructed based on what we see of x1, x2, x3, and so on and so forth. Whenever x1 is an odd, so we look at the first decimal place of x1. If it is odd, then we make this even, a 2. If it is even, then we make this an odd number 1. Is that okay? So the first digit of x, we intentionally make it different from x1. The second decimal place here is 1, so we intentionally make it different from the second decimal place of x2. So here we see that the second decimal place of x2 is even, so we are making it a 1 here. Okay, so we are constructing x like this, so on and so forth. Now, what we see here is that x is a real number within this range. And also, x cannot be any of the real numbers that we can imagine. X can have infinite length. X actually has infinite decimal places. But what we see here is it cannot be equal to x1, it cannot be equal to x2, it cannot be equal to xk for any k. So what does that mean? So it is a real number in this range, but then it is not listed in Goth or in your genius's corresponding way. So x is a number that is not listed. We have a contradiction because we claim that there is a one-to-one correspondence between the real numbers and the integer set, and then this means that any real number between 0 and 1 will be listed somehow. So any number will be listed. But here we find a certain number in that group is not listed. So we get a contradiction. So the contradiction comes from this one. And so that the original assumption, supposed on the contrary that it is countable, is incorrect. So that means that the set here, R prime, the set R prime here is not countable, and done. Okay, so that's all for what I want to show today. And in your homework that I just released yesterday, there is a question 5. So question 5 shows something that is very similar to this one, but it is a wrong proof because we are showing something that is wrong. So in that question, try your best to understand why it is wrong, because this will help you to understand the key idea of this proof. This proof is proposed by the mathematician Cantor. So, and because if you look at the green part, it looks like a diagonal of a matrix. So this is called the diagonal proof or the diagonalization proof. Okay, so that's all for what I want to talk about today. Yes. Yeah, that's true. Excellent. Yes. Thanks a lot. Let me see. Okay. That's the proof may have bug if the representation is not unique. Yeah, that's true. That's true. But in that case, we are actually having two numbers, two representation for the same number, or more representation for the same number. And still, our proof here creates a number which is officially inside the set, but it is not listed. So in that case, we still get a contradiction. Does that sound correct? So maybe we can have more than one representation for the same number, but still the key idea here, the key point here is that some number that should be listed is not listed. Okay? Yeah, showing something wrong. Very good. Yeah, the assignment question is something like someone gives a wrong claim and then proceeds with the proof, trying to prove the wrong claim is correct. So your target is to understand why the proof is wrong, so that you can tell your friend that, oh, your proof is wrong, so that it is not proving something that you are claiming. The claim could be right, could be wrong, but at least the proof is wrong, so it's not doing anything. So this is the assignment question. Okay? Okay, thanks all. Okay. So if you have any further question, please leave it at the questionnaire. And then thanks. Have a nice holiday. And then this assignment, I'm really very sorry that it is going to be the deadline will be next Monday, because I want to give out the solution during the tutorial. Okay, so thanks all for coming, and then try your best to finish it. I hope that it's not that hard. Okay, see you.